This presentation is going to be on MPLS and specifically the symbiotic relationship between MPLS and BGP. We're going to go over a brief history of MPLS and a configuration example. Now, this is a very broad subject, so I'm going to go ahead and skim through this, and there's notes on the slides that you can go back and pause the video and read it. This is the overview on the first slide. This is the overview of the MPLS network that I'll be using. Consists of one PE router, two PE routers, provider edge, and then two CE routers, which are customer edge routers. All of this is going to be taking place on Cisco Modeling Lab, CML. So it's a virtualized router environment, and that's where this topology is going to be configured and demonstrated. All right, so before we get into MPLS, we need to know why MPLS was needed. So in the 1980s and 90s, we began to have more interconnectivity between certain entities, schools, government entities, and all of that. And we needed a better way to interconnect autonomous systems together. With the advent of the ARPANET in 1982, they started using TCP/IP. More people started getting on the ARPANET. Then the National Science Foundation created a backbone consisting of 6 sites at a whopping 56K each circuit. So this backbone brought even more people, or more entities, I should say, into the what was then called the ARPANET. And we needed a way to facilitate all this interconnectivity and all these autonomous systems. Along comes Cisco, and Cisco was dedicated to creating hardware that would support specifically this interconnectivity and the protocols that support it. So they started with GGP, gateway-to-gateway protocol, EGP, exterior gateway protocol, and then that would eventually lead us to BGP. So in 1986, Cisco developed its first hardware router called the Cisco AGS that natively ran interconnecting protocols. BGP is often referred to as the 2 or 3 napkin protocol because it was literally designed in some napkins at a coffee shop between some employees of IBM and Cisco. What we have to know here about BGP is it was first published in RFC 1105 in June of 1989. And then version 4, which is the most modern version. Well, there's exceptions to that because they did some upgrades, but version 4 has been in use since 1994. And really, 1994 is really when BGP started being used and became popular. Then in RFC 3107 in 2003, that came out, and that was for BGP supporting label switching. And at that point, there was no MPLS, but it was already supporting labels, mainly due to Cisco's tags discovery protocol that they were working on. And then in 2007, we have RFC 4760, and this gave us the multi-protocol BGP. This is very important because it allowed multi-families like IPv6, VPNs. So that's the multi-protocol for address families. They call it IP address families, IPv6 and IPv4, VPNs, multicast, and all that stuff. So these two things, these two RFCs, RFC 3107 in 2003, RFC 4760 in 2007, is really what made BGP become useful to what was going to be later on MPLS. So MPLS, what is it? MPLS is multi-protocol label switching. And if you could see from this diagram, we have the MPLS transport, and it really can't transport all these protocols. You see that it transports Ethernet, ATM, PPP, DSL, and it was popular for a while to it would transport ATM, SONET, and DSL, but nowadays it mainly transports just Ethernet. And one thing to note about this MPLS, it actually derived from ATM, and even before that from frame relay, which used DLCs, and it was a form of a tag to identify virtual circuits. So MPLS uses the link discovery protocol, or the label discovery protocol, the LDP. But before we get to LDP, Cisco already had put in place TDP, which is the Transport Discovery Protocol. And from that, we went ahead and created LDP. And this all took place pretty much around 1999. And then the official RFC for MPLS came out in 2001, which I believe is RFC 3031. So again, TPD became LPD. So the Transport Discovery Protocol became the Label Discovery Protocol. And the Label Discovery Protocol, LDP, basically associates IP prefixes with labels. And when doing this, it creates what's called the LFIB, or the Label Forward Information Base. And this is what we forward packets on. You can see there that we have a sample of a MPLS topology with the P router in the middle at its core, the two PE routers, and then the CE routers. And this is basically what we have to work with Cisco Modern Labs. This is basically the same design. Now, if you look over to the left, we can see that there's the local tags here, and there should be sometimes there's outgoing tags, but you can see tag 16 is the label for this network, tag 17 is the label for this network, and so on. So it associates these tags with the IP prefixes, and it creates predetermined pathways. It's very important. MPLS creates predetermined pathways based on these paths and these labels, rather. So here we have LDP, Label Distribution Protocol. It uses labels instead of long prefix matches, which saves a lot of CPU. So traditionally, the routing information base was on the control plane. As you can see there, the RIB would get its information from routing protocols, IS, EIGRP, or SPF. As you can see, the link discovery protocol works. It first forms the label information base, which then moves that to the LFIB in a forwarding plane. So the forwarding plane really relies on control plane mechanisms to figure out the network, and then that gets transported it gets put into the forwarding plane as a form of FIB, and then the LFIB, the layer forward information base. And that's what we're going to be using with MPLS. We're going to go ahead and not look at the routing table as far as the IP prefixes, but look at the labels and where everything goes from label to label. LDP creates labels that are associated with IP prefixes. These labels create predetermined pathways across the network, referred to as label switch paths. LDP is responsible for label advertising and reception, and stores these labels in the label information base from the lib. In the traditional routing information base, we get the label forwarding information base. So it basically just explains what I said earlier. We use all these bases, routing information base, label information base, in order to get the LFIB. One of the important things, like I mentioned about a BGP, was support for labels, and then it got support for multi-protocol. That really was useful for MPLS. So MP BGP, multi-protocol BGP, does and has a symbiotic relationship, and it aids in label distribution through VRF VPN capabilities that it has built into BGP. So if you look at the left here, you can see my PE router, Pt.1. It has different customers, so customer B, customer A. And really what it does is it creates its own virtual router for each customer through VRF, and BGP carries these labels, as you can see here, and associates it with the prefixes for the customer. And one important thing to note is you can see here that we have a subnet or prefix that's the same, 10.100.200.0, 10.100.200.0. But these things are not, these prefixes never cross-connect. There's no IP conflicts because they're part of their own VRF. This one's part of VRF or virtual router forwarding for customer A, and this one right here is part of the VRF for customer B. So you segment the customers. That's one thing that MPLS using VRF does. And that's basically what I have here, explaining that to you. Another thing too, that's important to know, MP BGP or BGP only comes into place between the PEs. The P routers all run OSPF, and OSPF is not label aware. With the P routers, they all get their labels from the LDP protocol. The only thing that BGP does is transfer. So if, in other words, if you have customer A here and customer A here, it transfers these routes from customer A from one place to another, and whatever routes are on this end of the network will be seen on this side. So important to know that BGP only works between the PEs. So to recap, why MPLS? MPLS advantage: faster packet forwarding, label switching versus IP lookup, right? That's very important. We didn't really get into this, but traffic engineering, which is beyond the scope of this, but that's one thing that they use. Basically, traffic engineering, you can create your own virtual tunnels using labels, so better path selection. Quality of service, we saw that there is a header, and let me look at this header here. If I can go back, did I skip it? Yeah, you can see that there is a header here. So the header is 32 bits. You can see the first 20 bits carry the labels associated with the prefix, and then the EXP, this is basically the quality of service bits. And this is very important. It does its own quality of service. This is the S bit, which tells the router which label is the last label on the stack, and then the time to live. And it's important that we know where the MPLS fits. It fits between layer 2 and layer 3, the IP layer, so it's called sometimes the 2.5, the 2.5 header. So that's important for us to know. And again, going to the MPLS advantage, so traffic engineering, TE, quality of service with those 3 bits that we saw. Scalability, that's very important for customers. I mean, you can have one PE router now terminate hundreds of customers in the same router, and each customer has their own VRF, which is their own private routing forward instance. So basically their own private router, virtual router. Better security and VPN support, that's part of the VRF. Better network convergency because of fast reroute. So MPLS has this thing called fast reroute that you can enable, and it basically has the primary path with a primary label, and then a secondary path with a secondary label. So if that path, the primary path, goes down, it automatically goes over to the second path with, I think, less than 50 seconds, 50 milliseconds of delay. So it's very fast. Protocol independent. Again, it works with IP4, IP6, ATM, frame relay. Mostly, in this day and age, it works with just Ethernet. Improve redundancy and HA through LDP and RSVP. So that's the reservation bandwidth, I believe. LDP MPLS is flexible. It does more with the same resources compared to traditional routing methods, as it simplifies the core with edge intelligence. So basically, MPLS puts a lot of the heavy lifting on the PE routers and keeps the core free to be the core and do other things. So the PEs that terminate the customer CE routers is what does most of the heavy lifting. All right, and like I said, I use Cisco CML for this, Cisco Modeling Labs. I use the free edition, which gives me up to 5 nodes that I can work with. And this is the screenshot of what CML looks like. Now I had to get creative because I only have 5 free nodes, and I needed 3 routers to be the MPLS routers and then 2 routers to be the CE. But one of these routers terminates multiple customers, and I'll get into that in a moment here. But just wanted to see, show you what it looks like, and you can see the routers here on the bottom. I have the main P router here in the middle, and then the PE2 router here, which is this router, and PE1, which is this router. So here we get a better look at the network topology that I'm using. Again, as I mentioned, here we have the MPLS core. We have the P router that really, the P router just knows about other P routers and PE routers. It does not know about this customer here. It does not know about this customer here. The PE routers know about this customer. The PE router here knows about this customer and this customer, thanks to BGP that runs through between the PE routers. So the PE routers are aware of the customers. They're aware of the VFRs. The PE router is not. And here I had to get creative because, like I said, I can only have 5 nodes. Ideally, I would just put another router here, another CE router, but this one had to carry 2 customers, and this one is only carrying 1. And then what I do is I go ahead and I make sure that I can get from this customer here, customer B, over this network to customer B on this end. Then the same thing, customer A, I can get over the network and get to customer A here. Again, this over here, it's on a loopback. This traditionally would have been another CE router here, but due to the limitation of 5 nodes on CML, I couldn't do that. Quick comparison here, we have the edge router PE1 here, yeah we do, and then PE2 is here, and then we have the MPLS core router. Now, in the real world, you can have a lot of these core routers. I only have one here, and you can have a lot of edge routers. So right now, there's only one core router, the P router. You can have multiple routers. And if we look at this right here at the top is the OSPF. So OSPF is link state. They all know about the same thing, and that's a traditional routing table. So the P routers and the PE routers can be connected. But then if we look here with the LFIB comparison, we can see for router PE1, and this should be PE1 here and PE2, not P1 and P2. I'll fix this. But anyways, if you look at PE1, you can see that the forwarding table here, the LFIB, how it is here, how big it is. You can look at the one here for PE2, and you can see that it knows about customer B, customer A. But if you look at the same forwarding table, or you look at the forwarding table for the P router, the core router, it's very small. It only has labels for the attached routers, and the attached routers in this case are PE1 and PE2. And then here we have CE, we have the MPLS multi-CE, which is this one right here, and then we have CE2, which is this one. So if we look here, if we do a trace route, and you have to specify VRF because this is a VRF, a WARE router, where this is not. You don't have to specify VRF, but this one is because I'm terminating multiple customers. But if you do a trace route here from customer B on this router, this CE router, the multi-CE router, to this CE router, you can see that it goes through the various links. The first one has no label, and then it goes through the core, and then you can see the labels here, 16, the inner label, 22, the outer label, and then it gets here, 22 is the outer label. It pops the label and delivers it to the router that terminates customer B, which is that actually terminates this right here, this prefix on this router here. So basically what this trace route is showing you is that it's going over this network here. And even though this P router is not aware of anything, it allows it to go over this network based on the labels. And then once it gets here, it looks at the VRF, right? And it says, okay, yeah, this VRF is for customer B, and allows customer B traffic to come in and go out if it has to. All right, that's it for the slides. I'll go ahead and take this now to the actual lab on Cisco CML.